It's time for our last speaker of the day. Chuang Gan is with the MIT-IBM Watson AI Lab, who happens to also be in this building, and also recently joined UMass Amherst as assistant professor.
Yeah.
So brand new a member of UMass Amherst, and he has tons of work on robotics and multimodal approaches, and including sounds. So he's gonna talk today to us about learning to perceive physical scenes from multisensory data.
All right. So hello everyone. So I'm Chuang. So it's my great pleasure to speak at SANE. Actually, I first participated, I think, back in 2018, when I was first year postdoc with Antonio and George Tenenbaum at MIT, and it's really wonderful that I can. 4 years later, I can talk about some our this year's efforts on trying to integrate the multi-sensor data to enrich the physical scene understanding. So, as we all know, that the deep learning is very powerful. That it enable. Oh, okay. So we all know that deep learning has revolutionized many fields, that including the object detection, video recognition, machine translation, as well as speech recognition. And the success of this kind of perception task that enable us to thinking that maybe this kind of deep learning approach already achieved the human level intelligence. But on the other hand, there are several reasons as well to resist the temptation. First, so we all know deep learning is really data hungry, that it requires massive label data for model training, even though there are some recent progress on self-supervised learning. Secondly, it always have a limited ability to adapt to new scenarios or new concepts. So this system essentially are very different from human intelligence in terms of data efficiency, generalization, and flexibilities. So here in this video, you will see that how a baby trying to learn about the world. So he seems doing something a little bit random, hanging cups together, making snacks, knocking them over, and hearing the and also hear the sound. There may be a few things her parents taught him before, but mostly she probably in her own. So how could she grow man from such little information? So one thing that she can leverage all the science to figure out how things work. For example, he can associate how this cup look like, and with how it will feel, and how it will feel with how it sounds. Essentially, he's building a causal model about the world, and allow him to imagine what's going to happen and apply action accordingly. So, and also there's many theory from psychology and cognitive science have indicated that the human can naturally attain that kind of multi-sensory data and arrive a rich understanding of our physical world. However, in AI, we can see that much more attention, especially in the computer vision community, they pay attention to how a single modality can drive learning. And for example, most of state-of-the-art computer vision systems right now are always using vision information alone. But actually, there are a lot of information that sound can give us. I mean, for example, when we see the table, it might be hard for us to imagine what it's made of. But we can hear the sound of this one. So you can hear the sound of this kind of physical interaction, that we can make that actually it's made of plastic. And also in this images, actually I want to ask questions. So how many people think this baby have trouble? You can raise your hand. Okay, and how many people think this baby is okay? Okay, so yeah, actually just from the image it's really hard to tell, but when we hear the sound. So you can collect from actually this baby is playing with his dog, and also she's fun and she enjoys the time. And also sound can also tell us a lot of information that go beyond the vision. For example, in this case, that even we haven't seen anything yet, but when you hear the sound, you can imagine that there's just true environment. So sound can actually tell us that tell a lot of information before vision signal arrive. So in this talk, I will pretty focus on to answer one question. So can we connect with vision and sound to enrich the machine perception? And in the first talk, I would like to talk about actually, it's also the first project I work at MIT on in this area. It's a task we call it as visual sound separation. So this is a joint work with Dr. Hang Zhao, now it's assistant professor at Tsinghua University, and also Professor Anton Turba at MIT. So we started working on the domain about 3 years ago, and the problem we want to solve that given the kind of music performance video, and we want to separate the sound played by different musicians. So previous work from the audio community, they always using the kind of audio line to do that kind of blind sound separation. So this is very powerful and work very well on some speech separation scenarios. But we feel it's still very challenging to generate to a much more natural sound for them, the music. And the idea here is that we try to think whether we can connect vision with sound and to learn from the music video and self-supervised to localize the sound source and separate it from the mixture. And as the first step, we created a large-scale music performance video data set that we called as music. So the data set cover around 1,000 musician instrument video or 20 video categories. And the core idea we're trying to do is that we're trying to create a synthetic training data set by mixturing arbitrary sound source from different video clip. So an example of this kind of mixture, can we hear that one? And then the goal of the neural network that we're trying to separate the audio track from this kind of mixture, but conditioned on its visual input. So even though this network are trained in a supervised way, but actually we don't take any label of how this mixture sound because we create a synthetic mixture. So we call this framework as the mix and separate self-supervised learning framework. So concretely in this mix and separate framework, that it contains the visual analysis network, audio analysis network, as well as the audio synthesis network. So the video network basically parse the video frame that contains the musician playing the music. And the audio network takes this raw waveform and we transfer it as it's the sound spectrogram. And then we're using UMass style architecture to encode this kind of feature into different channels. And finally, we condition this visual feature with this kind of sound spectrogram feature and learning to estimate the mask. And then we multiply the mask with the input sound spectrogram. We get the target sound, the sound component, and then we can using the sound spectrogram and combine with phase to reconstruct the original waveform of the separate network. But then in the testing time, we can either take a video clip as input to separate its corresponding sound, and you can also take a region of features. So for them, you can click a pixel and put into this network and trying to imagine what this pixel sound like. So here are some demo. This is the input video here. And if you want to clip the pixel of this guitar, so what we will hear? And also we can try to click pixel of another instrument, what will happen here? And you might be wondering that what will happen if I click the pixel of the bookshelf? So you can see. Yeah, over here, nothing. This means that this network trying to associate the region and the visual region with how it will sound like. So here's another example. So there's also two people playing the instruments. This is the original video. And by clicking the piece of the trumpet, we can hear. And we can also try to click piece of guitar. And also we can try again to click the background wall. So there's nothing happen. And with this technique, actually, we can do something more fancy that we can do the kind of music remixing, or we call that kind of audio acting through pixel. So, I mean, for example, in this case, take this video as input. We can actually adjust the volume of each individual audio. So it adjust the volume of each individual instrument. Here, example. So if we want to make the live instrument a little bit louder, right, a little bit louder, okay. And we can also do the reverse one. So even though in this case that they did a pretty good job, actually this doesn't have the limitation. So here I will show a very interesting failure case here. So in this video, you see two people playing the same instrument. So when we put this system in a kind of somehow pixel system, actually the system did nothing. Basically, it's very hard to tell from pixel how different the two people playing the instruments. How we can solve this problem? To address this challenge, we propose a new feature called music gesture. So basically, we're trying to identify a melody by starting the human body language. So the music gesture is that kind of human keep on coordinate about how human interact with the instruments. So we use that kind of structural keep on representation to drive the audio network to separate its corresponding audio source based on the human body motion. So here are some comparison results. So this result is an older system that using pixel and output flow like the kind of rough motion feature. And apparently it did nothing in this very challenging case. But how about we using the music gesture? Okay, even though it's not perfect, but you did some very reasonable good job here. And here's another example. So again, the prior system did nothing in this very challenging case, but how about our system? Okay, so here's another, my favorite example of two people playing the piano. So they did nothing. How about ours? Okay, so how about we move to much more challenging case? So if there's multiple people playing the same instrument, what will happen? How robust of this kind of music general system? So here are the people, there are 4 people playing the same instrument. It did a really wonderful job in this kind of case. And we also trying to understand that what's the system actually learn. So we have a very interesting observation here. So we're trying to visualize the attention map of this kind of human body key point. So we found that when we separated the sound, for example, of guitar and the flute, so the model focused more on the key point of the hands. And when we're trying to separate some silo or violin, and they are trying to pay more attention to the elbow. So if you see the pricing is that represent the attention scale of people keep on. Also found that actually this model indeed learn how to associate the human body keep on and how it will sound like. And here's another example that people actually is so actually the woman that she's making 2 different kind of sounds. So our music gesture system, because we have the kind of implicit human body keep on how movement, and we know which point learning as how it will sound. So it can separate the upper body and the lower body sound. All right. So here I'm going to talk about how we can using visual signal that to separate the individual sound component. You might be wondering that why we can do much more ambitious. Can we generate a piece of music based on the human body motion? So in follow-up work, we're trying to take a video like this one and generating a plausible music performance video. So actually it's a very challenging task because basically we need to align the visual and audio components. And there are actually 3 things that matter a lot. The first that is about visual perception. So how we can identify the human and the kind of musical instrument alignment. Secondly, we also need to have audio representation. Basically, it's very easy to predict and also can encode some music rule that some symbol rule that already encoded that kind of music structure. And thirdly, of course, we need that kind of a powerful model that connects that kind of 2 different representations. And for the first part, that we currently using the human body motion or the music gesture we introduced in the first part of my talk. So basically you have the key point, you can implicitly know how the human body interacts with the instrument. And for the music representation, we choose to using MIDI. This actually is a kind of a symbolic representation that can encode that kind of note event information, for example, some note on, note off. And then given a pair of keep on and MIDI event, we are trying to associate them using this kind of a transformer framework. Basically, the transformer take the keep on as input and trying to predict the MIDI. And then we can take the MIDI as input and we can use an audio synthesizer to generating a piece of music. So here are some music generation results. Another example. Here's the guitar example. And also since we have the kind of MIDI representation that actually allow us to do this kind of style manipulation task. For example, in this case, you can see different pitch Here's another example. All right, so I would like to do a hard stop here and to take 1 or 2 questions before I move into the second part of my talk. So any question here? Here.
Hi, so what I was wondering is, in the case, I don't know if you tested this, and if you haven't, that's cool, but if you had, say, a Kabuki area where everyone's playing instruments in, say, triads, for example, but they're playing the same rhythms, what happens?
Sorry, I don't think I fully understand. So
if you have a set of instruments and they're playing all the notes in unison,
mm-hmm.
and if the pitches are different, they're 2 different pitches, what happens?
Yeah, this is a very good question. The answer is I don't know, and probably it will not work. So and I actually we found many. So actually we have tested this kind of music sound separation system on some outshore system. So actually the system will not work, but the main reason is because they have the room impulse response. So very complex vibration, and our model trained on this kind of web video. We do the mixture and we do implicit capture the kind of impulse response, so the system clarify on its outshore. But on the other hand, I feel that if you have more data augmentation, you can simulate some impulse response and to generate more complex data, much more data manipulation. It might work a little bit. Yeah. So go ahead.
You had that case with the piano where it was an octave part.
Mm-hmm.
It was, up until the very end, just before the end, they were all both playing the same notes.
Mm-hmm.
So how would you say that was able to figure out which one was playing?
Yeah, it's a good question. Maybe I don't know actually. So, but we do find we do try to figure out. So we do try to have some calibration to do that. We do have some quantity evaluation doing the kind of piano sound, so by using some synthetic mixture. And the model, I think it's not that kind of perfect. I think for imagine for dB, I think 4 or 5 that can solve. So it's not perfect solve the problem. But in some case, we can do some okay job, but this still is very challenging problem in general, based on the visual signal or not. Yeah. Mm-hmm.
Are you also modifying the video so that the keyboard is correct?
It's all the same video. Yeah, it's all the same, but we just adjust the key of the version. All right, so I will move to the second part of the talk. So most about how we can, because sound is also about the physics. So I will tell about the effort from MIT that we're trying to better connect with sound and the physics. And the first thing I would like to mention is the kind of CD World platform. Actually, this is led by Jeremy and Sis. They are wonderful Unity game designer. So basically, this kind of multimodal physics simulation that he can render the kind of photorealistic scene both indoor and outdoor, as well as we can do this kind of physics trigger sound. Actually, this part is led by the George McLaren team. I saw Vince here. Vince is part of George team, and James, he used to be a postdoc at MIT. Now he moved to OSU as professor. So there are a bunch of people behind the simulator. We're trying to print both that kind of sound reverberation as well as the physical trigger sound. So basically, we're trying to, based on the physical property object collision, we can simulate the kind of impact sound. Here is the example we have. And this simulation also supports the kind of physical simulation. You can do both rigid body and soft body simulation. And also we have the robot acquisition and the humanoid agent that can incorporate platform that can interact with the kind of physical environment and by leveraging multi-sensory data. It also incorporates kind of VR scenario that we can using. So we incorporate kind of Oculus high side, which Oculus Touch controller that we can. So in the video, you can see that we trying to control this ball using our own hand. And the most exciting part would be trying actually related to this work that we build a brand new data set called fallen object data set. So basically, we're trying to simulate around 8,000 objects fallen on the ground and trying to estimate their physics under based on this kind of auditory event. So the object can fall anywhere. So for example, it can be fall down on the floor, on the shelf, or even on the pen, or on a ball. So it can fall down anywhere. So the task here that we're trying to have a robot engine that hears the sound and trying to find which object and where it fall down. So this basically, this robot engine trying to do an inverse physics problem that based on the audio, he needs to figure out how visual, physics, and audio happen. So we're trying to have this new data set that published on this year's DPR to invite people think about how we can better compare with the kind of perception with physical understanding. So here is the example of the task. So you will first hear the object drop down here. And then a robot agent trying to based on sound to figure out roughly where this object fall down. And what this object might look like by connecting his visual information, audio information, as well as the physics knowledges. So this data set has already been publicly available and feel free to download on our website. And I think another thing I want to mention is that you probably know that all this kind of physics simulation or sound, either the sound space habitat the mentioned by Orin and also our cerebral simulation. So all this kind of sound simulation probably they're always using a computation-based approach to model sound propagation as well as the impact sound simulation. So they did a really wonderful job and also dominated the kind of sound simulation community for a couple of years. But as we all know that the neural network has been anywhere. So our idea is that I think whether we can also revolutionize the kind of sound propagation, impact sound generation using neural network, using some industrial barrier to model the sound propagation. So this is a paper we just published on the Neurips this year. So named Learning Neural Acoustic Fields. So the idea is very simple. We are trying to see whether we can use the neural implicit representation to capture how sound propagates in a physical scene. So we are thinking that so I think probably many people know that there's a very similar thing called NERF in the visual community. They're trying to using the kind of neural rendering to replace the kind of graphic agent to do the multi-view. Here our idea is that whether we can apply this kind of neural network, leveraging the inductive barriers to capture sound propagation and learning from data. So this is our idea. And the network actually pretty simple. It's very it's actually inspired by the success from NERF, neural scene representation, that basically we take the coordinates of the sound emitter, and also because in the visual part we have a sound emitter and also listener. So we take the coordinate of sound emitter and the listener, and we try and fit this coordinate information into a neural network. So the neural network is an 8-layer MRP network, and we trying to predict. So we trying to fit an impulse response. And we also incorporate some other techniques to better capture the continuous of the scene. For example, we propose using a kind of local feature correlate. Basically, we can in each correlate, the coordinate will share a local feature. So this can guarantee that to do some local consistency when we do this kind of sound impact sound prediction. So when we have this kind of neural representation, even though they learn from sparse location, but the neural network can learning this kind of continuous function or we call that, so that's a neural field that will allow us to render the audio at arbitrary location in the scene, even we take the sparse data as input. So here's the result I want to show. So basically we're trying to render the kind of spatial audio at arbitrary location in a room.
Sometimes I just sit down and she starts so people walking by. I see all the different kind of faces, people all around the place. You're wondering why I just smile, just smile, just smile, just smile, just smile, just smile, just smile.
Yeah, this is roughly like how we using a simple neural network to capture all this kind of room impulse response. Okay, so I think I have a few minutes left. Maybe at the end of the talk, I will talk about another domain that we're trying to also connect with sound of physics about to thinking sound actually as a causal event, causal effect as a physical event, and how we can use this physical event that drive, for example, reinforcement learning as an intrinsic power to do the operation. So as a starting point, I want to show this very popular Atari game. So okay, here, so okay, watch the video first. So actually, the sound information tell us a lot of what happened in this game. So here's another example. So actually, yeah, feel that actually this audio signal that can tell us many information about the game. For example, the dining event and also how they win the game, something with some goal. So this motivates us to think whether we can using this kind of sound information as an intrinsic reward to drive the R operation. So this actually very similar to the first example I showed in the baby deploying. So he's trying to make some noise, make some sound to learning more about the physical world. So in this reason, we build a noise agent that we're trying to building a exploration agent by leveraging the multimodal cues. So the approach here that we're trying to first to define the auditory event prediction framework. So we first ask the agent to interact with the environment and to collect a bunch of data. And based on the audio information, we can use k-means to cluster the audio into different auditory events. And then the machine agent will try to predict what happened next by comparing whether he can predict the auditory event accurately or not. So essentially, if the agent understands the world very well, he can predict all this kind of no event very accurately, what happened next. And if he doesn't, means that he needs to explore more in this scenario. So here's the result of visual exploration result on 20 Atari game, contain the sound, of course. So we can see that by using this kind of audio information, so the top one that can orange curve is the R curve that using that kind of audio information. We find it can learn this thing much faster than only using the visual cues. This actually inspires a lot of how we can better leveraging that kind of multi-sensor data to build a kind of generalized agent. It's also related to how we build a kind of embodied agent that can actively learning from multi-sensor and also get some very interesting behaviors that how to interact with the world more intelligently. So here are some visualization results. So we can find that by using the audio information, so the agent can earn much more reward than the kind of only using visual signal line. All right, so I think this will be the end of my talk. And finally, of course, I need to I can acknowledge all my collaborator, that's my MIT advisor, Antonio Torba, who bring me to this area, as well as George Tenenbaum, lay out many foundation to connect sound and physics, as well all the, and also George McDermott, that he teach me a lot of things that about all the simulation, and also all the wonderful students. Hangzhou actually is, when we start working on the topic, actually he's the 4th year PhD student that start to enter this area. So a bunch of people working in that area to push the audiovisual learning. Okay, thank you for attention. I think we still have time to take a few questions in the second part. Thank you. So I guess the question will go to this part.
So what do you think are the challenges that are still left for this? I mean, I'm very excited by the Neural Acoustic Fields learning paper, and what do you think what is left in terms of challenge in terms for this kind of approach?
Yeah, so actually there's a lot of things that we that probably I would say at least one of the first, I think probably the first one I trying to using neural network to learn this kind of learn the sound propagation, and we do meet several challenges. First, we find it very hard to predict the phase. The phase actually is very essential to that kind of sound localization, because you have say different trying to do that kind of special localization. So phase, how to represent the phase and how to predict the phase actually is we don't do a very good job here. The second one that we in this work we're trying to only predict the impulse response, and the nature of that how you can directly predict the audio, because impulse response is not that rare here. You have to get from simulation or calculate from something, but how you can correctly take the natural audio as input and to try to do that one. And the third one actually I think is also open question even in the nerve community, is about the generalization, because currently we using one neural network to fit one thing. How we can either learn from very few data to adapt to new things, how we can represent the thing to one foundation model for them. If we have a lot of foundation model, we can take accuracy and do generalization. This still open question, but I do think that's a kind of neural idea that can revolute the field a little bit. That it's also much more broader applicable. One benefit of this one, we can represent the impulse response in a very small neural network. So we can save this kind of space very in a very small neural network. You can record all the room impulse response. Otherwise, you need to download all the. Probably people have to working on some space data side. So even download the data set, it will be 3T, I think. But here you maybe 100 B. You can download the thing here. So that's a big benefit about storage things here. So I think there's a lot of opportunity for Metaverse that this framework will open.
Let's thank Chuang again.
Thank you.